Good day, Algebra 2. Today we start Chapter 13, and the first section we're going to look at today is Section 13-1, looking at exponential growth functions. And it's going to be a nice section. Nothing new in here, just a different looking type of graph. Again, we're going to be using everything from the HD&C material we used before. So let's start off first. Well, what is a exponential growth function? Right here, y equals b raised to the x. This is an example of an exponential growth function. But more importantly here, your b here, that's your base. They give this to you. Your base will be greater than 1. So in other words, we're going to be probably doing examples like the base is 1.5, base could be 2, base could be 10, base could be anything as long as it's greater than 1. And at the same time, this is the parent function of the exponential growth function, and here is the transform one. Again, everything just by me saying transform triggers your brain saying, we have to do that stuff again? Yep, we need to. Now, a good tool to remember is some of the stuff that we've learned throughout the year is found on pages 2, 9, 10, and 12 of your HD&Cs. Again, like I said, this is all review, nothing fancy, but the big ones we'll probably run across here is finding your x-intercept. Again, your brain's already thinking, what is an x-intercept? Oh, now I remember. Now remember, an x-intercept is where the graph of the function intersects the x-axis at the point of x. Again, this is nothing major. Here you take your function, let y equal 0, and solve for x. Again, this is where we have to use a little bit of our algebra concepts. I think you'll have no problem, okay? Then finding the y-intercept. This is where the graph of the function intersects the y-axis at that point y. Again, you let x equal 0 and you solve for y. A lot of this part right here is just mental math. You can do that. Then the two other most important ones that we've been dealing with since Chapter 1 is the domain and the range. Now, once again, the domain is all those values of x that we can plug into our function, and they got to exist. Sometimes there are some values of x will not work in there. We did this before when we did rational functions. So the domain is those values of x that we can plug into the function. Now the output, okay, doing your order of operations on your function, the output is your range. That is the set of all functional values, or the values that come from plugging your domain into your specific function. So these top four are the ones that you guys are going to be really familiar with in this section dealing with exponential growth functions. All this other stuff is for other types of functions. So again, let's go back up to page 9, 10, and 12. But I'm mostly going to focus on page 10. Page 10 is the top part. You're probably going to say, oh, I remember those. That's the top part. This right here gives you a lot of information about your function, your transform function. So as a quick review, just so you can see it, K, that is going to be your vertical movement. Is your function going to go up or down based upon the reference point? Again, H is your horizontal movement. Is it going to move left or is it going to move right? Again, over here to the right, they tell you if your value of H is greater than 0. Okay, in other words, you got to just look at the H. Don't look at that negative sign. You got to look at the H. Like if H is 2, we know it's going to move left 2 units. But if we notice here the H is a negative value, okay, this takes this to be a negative becomes a positive, that's going to move to the right. Again, all that stuff I'm saying is nothing new to you guys, okay? The coefficient in front of your x, that is going to be your horizontal compression or shrinking. That's down here. If there's a negative sign in front of there, that has to deal with a reflection across the y-axis. That's taking the function from this way and flipping across the y-axis. Again, keep going on. Your A is your vertical stretch or compression, depends on what A is. Okay, that's this part right here. But if there's a negative sign in front of it, that is going to be reflection off the x-axis. That means if the function's going this way, it's going to flip down this way. So again, all that at the top part here deals with transform functions. All right, now if I go to page 12, down below here, this is what the parent function of an exponential function, a growth, exponential growth function looks like with a base of 10. That's what this one looks like. We'll worry about this one, a base e, at another section. Okay, so this has to deal with a base 10, and you're going to be seeing that it's going to have this form. And this point right here is your reference point. It'll make sense when we do it again. Okay. All right, HDNCs, let's put it away. All right, so going to the Explorer 1, okay, an exponential function is a function whose form is f of x equals b to the x, where the base b is a positive constant other than 1, and an exponential and an exponent x is a variable. Now, this one is just base is going to be greater than 1. Now, when we get into problems where the base is between 0 and 1, that'll be the next section. That will be an exponential decay function. All right, trying to make it as simple as possible. In the Explorer A, here is, again, if you think of this as your t-graph, these are the elements of your domain plugged into this exponential function that has a base of 2. And we get all the values here. Use your calculator for that. This one is exponential growth function, has a base of 10. Plug your values of x. Again, you notice here that they have the same elements of the domain. So that tells you right off the bat that the way this problem, any exponential growth function works, it can take on any element of the domain, from negative infinity all the way up to positive infinity. So this is the y values, or your range. And down below, I took the time and I graphed the parent function of 2 to the x and the parent function of 10 to the x. Now, the whole purpose of doing this is letting you see that an exponential growth function always takes on this type of a form. But the only difference is what happens with your base. Now, again, you're going to notice how this one is not the base of 2. This one is not as steep as a base of 10. So in other words, this function right here could have a steeper graph if the base here was greater than 10, like 100. Now, again, you'll notice here on this one here, as my base gets smaller and smaller, this function starts being a little bit not as steep. It can go, as a matter of fact, get close to 1, but never touching 1, because if it becomes y equals 1 to the x, it's going to become nothing more than a straight line. So again, we're dealing with this section. So think that through, be no problem. All right, the top part of the Explorer, it just goes into what is the domain of the parent function of base of 2, what is the domain of the parent function whose base is 10, then what is the range. Again, going back to these examples, okay? Okay, you're going to notice that any value of x I plug into this function, I'm going to get a y value. That comes from the range. Excuse me, that comes from your domain. But the output, okay, you're going to notice that as I start plugging numbers to -5 to -6, it gets closer and closer and closer to y equals 0, and it never touches it, okay? So the domain in this case, for this particular example, the domain is all values of x, but the output will never reach y equals 0. And we'll remember that as a horizontal asymptote. You'll probably remember that one, okay? All right, so now let's go into more details of these problems. At the top of page 437, the problems they give of here is they're going to show us the reference point and their asymptotes are going to be labeled. All right, now this first block right here is an exponential growth function having a base of 2. The second one is an exponential growth function having a base of 10. Now what I did on the left-hand side is made a little t-graph, and I just picked a few points, plugged that into the function. So if I took -1 and plugged it into this function, again, you're more than welcome to use your calculator. So 2 raised to the -1, that'll give you 1/2. So in other words, when x is 2, all right, so when x is -1, we see that our y value is 1/2. If you let x become 0, you get 1. If you let x become 1, you get a y output of 2. Again, you'll get an idea of what this function is by graphing it using the t-graph. Now, I highlighted the reference points for base 2. It's 0, 1, and 1, 2. Did the same thing over here with the function 10 to the x. Again, this one has a reference number of 0, 1. Now, I'm bringing that up is because when we go into a transform function, you know, what is happening? Well, again, this is the shifting part right here. Up 1. Okay, well, it all depends on what how the function is set up in the transform part. Then this distance right here, that's your vertical stretch. This is your horizontal stretch, and it's all going to be based off of what we plug into the function or just by looking at it. Again, I'm just going to keep this very simple. Again, I am not going to go into details on graphing it. I really would love you guys to get dependent upon your calculator just a little bit. Okay, so let's go down below. In explain 1 or example 1a, they have this parent function right here. G of x equals -3 times the quantity 2 raised to the x minus 2 plus 1. Now again, this one tells me right off the bat that the parent function, okay, the parent function is f of x equals 2 to the x. So in other words, this function right here is going to take on the shape, better move this down a little bit, it's going to take on this shape right here. Now it's going to be a little bit different looking. It's only because it's going to be shifted and stretched or compressed or reflected, all because of your information on transform functions. All right, what I did is I took the transform function and I wrote it over here. And all I did is I just identified some of the key things of that parent function. Again, we see that the +1 is a vertical shift of, oh, wow, made a little mistake there. It's a vertical shift, again, of 1 unit. I just caught my mistake. Bifocals are not working today. All right, so this one has a vertical shift of 1 unit. So in other words, if we were looking up here at the parent function, okay, this guy has now just shifted up 1 unit. All right, next thing is this part right here is the bx minus h part. So the h is 2, so it's going to have a horizontal shift to the right 2 units. Again, there is no value of x, no value in front of the x. That's going to be the b there is going to be your horizontal stretch. There's no negative sign right here, so that's not going to be reflection off the y-axis. It's not going to flip, okay? Then we go over here to A. The A is 3, so that tells us we have a vertical stretch by a factor of 3. So in other words, if we go back up to the parent function, this right here has a vertical stretch of 1. Now, this stretch now is going to go 3 units. So 1, 2, 3. So instead of this point being right here, it'll be up here. It's going to stretch. It's going to stretch. Then the negative sign in front of the 3 tells us this is a reflection off the x-axis. So that means if we look at our parent function, this one right here, again, I can't do my hand this way. This guy, this function right here, parent function, he is going to be rotated this way. That's why it looks this way. All right. Now again, this part right here is just giving you a description of what is happening to this parent function. That's important to know. Again, at the same time, don't be afraid to use your calculator. So we've done this before. So if I take my calculator, went to the graphing part, again, I'm going to go and plug in the parent function. And then down below, I'm going to write down the transform function. Now be very careful on how you plug your values in, because mistakes will be made. Oops. Okay, I've got to get it set up so it looks just like this. Now I did not have to, but I put parentheses around this x minus 2. All right, so now we're ready to graph it. So you hit graph. It's thinking. Da, 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 dun, 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 dun. All right. So the blue here is your parent function. The red is the transform function, and you'll see that it's been rotated. It's got a little, again, you can look at it and base it upon that. All right? So the next thing we want to do is, let's go to the next page, and just basically the same thing again. I'll let you guys take a moment and write this information down. I graph the parent function. It's not as good as the other page. And then the red here is the graph of the transform function. Now your book uses other things in here. You're more than welcome to do it this way, but I think once you have familiar with how each part of the A, the B, the H, and the K, that should help you more than anything in graphing. So you got to remember to do that. Okay, all right, let's move on. Now, in the year turns, I did not graph any of these. All I did is I just took the transform function and I just identified what A is. It's 4. I identified what H is. H is -2. Remember now, back into the transform function part, the way it's set up, is causing me, let's see, power. Okay, it's your base, parentheses, x minus h plus k. Now again, remember now, it's got to be in this form of x minus h. Now that's why this is a -2. It's not set up in that form. So if I was to rewrite that into that form, it would be x minus a -2. Because I know a -2 makes it a +2. Right, we've done that before. You should have no problem. Identify what k is. And we know now we have a vertical asymptote of y equals -6. Now remember, that always comes basically from the range, or you can just focus on the value of k. The value of k is going to tell us what your vertical asymptote is. Now again, if you forgot what a vertical asymptote is, we know it's y equals -6. So we know this graph will get close to -6, but never touch it or never go through it. So that's your vertical asymptote. It's all dependent upon K. All right, letter 5. How about number 5 from the year turn? Once again, I just identified what my A. This part right here deals with the negative sign in front of A. I identified what H is, I identified what K is, and I asked myself what the vertical asymptote is. And all this information is nothing new. You guys can do this stuff. Also, get yourself in a habit of using your calculator. I have no problem with that. Again, we know that this is a y asymptote of -3. So we know that this function, when we graph it, will never touch that line. And since this is a negative sign right here, this is going to be a reflection off the x-axis. So instead of being the function going this way, it's going to go down this way. I'll let you experiment using your calculator. Again, this one is the parent function is y equals 10 to the x. Number 4, your parent function is y equals 2 to the x. I'll let you do some experimenting with your calculator, and you'll be able to see the difference. All right, now the next part is something that we really never got into, is they just give you bits and pieces of the function, and they wanted us to write the equation. Again, not important for right now. I do have another one in here, but it's not part of any of your homework assignments, so I'll just not cover that. All right, now again, just to go back over again, this part A from example 1A, this guy right here should help you out immensely in graphing it. Again, just identify the key features and use your calculator to graph it. Okay, I don't mind if you want to try and graph it on your graph paper here, that's fine, but try to see what makes up this function and graph it using your graphing calculator. All right, so I'm going to stop there. I think I've talked about exponential growth functions. And the reason they call them they're growing is because your y value is growing and increasing. Your y value is increasing. We'll see how this is really used in a later section, because exponential growth functions are going to be used when you get into chemistry or when you get into biology, especially when you're looking at the growth of fruit flies or the growth of bacteria. Or you can also see this in the financial world. Again, everybody likes to see their 401k increase. That's all based upon exponential or just a growth function, not necessarily exponential, but a growth function. We'll look at those examples later on. All right, guys, hopefully this was very helpful for you. Again, go on back to page 12 if you forgot everything that we've talked about. Not page 12. Let's probably do this the correct way. Page 10. Everything that we talked about is up here. And honestly, this is going to be, after doing this like the 7 millionth time, it'll probably make a lot more sense as we get into it. All right, once again, if you need any help, get in contact with me. Love you guys. Catch you later.